Hello and welcome, everyone. My name is Lauren Harrington, and I will be your host for today's webinar. I'm being joined by Dr. Lauren Biddle and Walt Cooney, who are here to discuss a very ambitious observing campaign and answer all of your questions about ways that you can make contributions. It's promising to be a really fun webinar, but before we jump into it, I have just a few quick housekeeping announcements to make. First, we are running Zoom in webinar mode today. Go back to that slide, which means that you get access to a few special features. Most important is the Q&A button, which is located in the Zoom window at the very bottom of your screen. When you click on the Q&A button, you can type in questions for our guest speaker, and I highly recommend that you do just that. After today's presentation, we'll have an extended period of question and answer so that we can get to all of the questions you guys have submitted. Another button, which you can find down there in the toolbar at the bottom of your screen, is the CC, or Show Captions button. When you click on the CC button, you can enable or disable Zoom's automatic closed captioning. It's a useful one to have in your toolkit. Next up, a shout out to one of our monthly webinar series, the one which is sponsored by the National Science Foundation. It is entirely in Spanish, including the title, which translates to The Science of the Sky for Beginners. Each webinar introduces basic science and astronomy concepts and provides opportunities for casual discussions between presenters and participants. It's totally free and aimed at the general public, age 12 and up. The episode all about exoplanets is coming up on December 16th, and we will have one more broadcast after that in January. Please feel free to spread the word to your Spanish-speaking friends and colleagues. And now, back to the webinar at hand. Our 2023 webinars are sponsored by Boyce Astro, and we would like to take a moment to thank and acknowledge them for their support. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Alrighty. Our speaker today earned her PhD in astronomy and planetary science from Northern Arizona University and is now working as a postdoctoral fellow in the Department of Astronomy at the University of Texas at Austin. Her research involves studying key signatures of magnetic activity in young stars, such as protoplanetary disk accretion and flares, in order to improve our understanding of young stellar activity, as well as how magnetic activity may affect the evolution of protoplanets. Early this year, she and some of her collaborators at the University of Texas partnered with the AAVSO to launch an observing campaign targeting AB Aurigae, an active young stellar object with intriguing features in its disk. Today, she's joining us to share some more information about AB Aurigae, including how your observations have been used so far and how you can continue to impact the study of this fascinating system in the future. It's promising to be a top-notch talk. And so with that, I would like to go ahead and introduce our honored guest speaker, Dr. Lauren Biddle. Welcome, Dr. Biddle.
Thank you so much. All right, I'm going to share my screen here. I really appreciated your title slide because it was the perfect transition into my slide describing the target of interest, AB Aurigae. AB Aurigae is a young Herbig AE star. Its age is about 4 million years. Spectral type A0. It's about twice the mass of the sun, and also twice the mass of the radius. And it's really hot. It's got a temperature of about between 9 and 10,000 Kelvin. So on the left here, we have an image by Boccoletti et al., which is just a really beautiful image that highlights the structures that we see in the circumstellar disk around AB Aurigae. This image was taken with sphere in scattered light. And one characteristic that's particularly notable is when observed with ALMA, shown by this image by Tong et al. 2017, we have identified potential locations where planets can form, particularly one highlighted by these blue arrows here. And so we Thane Curry et al. In 2022 had followed up on these observations and with the Subaru telescope and had imaged AB Auriga and found the at that location where we would have expected a planet to be based off of the disk morphology, they identified a protoplanet candidate, AB Auriga B. However, we need to always follow up and confirm exoplanet candidates. And one way that we can do that is by searching for accretion shocks that can occur on the protoplanet itself. With it being embedded in this disk of gas and dust, we would expect it to accrete the material around it. And so here on the right, I have like a sketch of what that might look like on the surface of the star. We've got material falling from the circumplanetary disk, in this case, that would form some sort of accretion shock that gets really hot and can, for stars at least, I have here written that it's very hot, a few million Kelvin, maybe not so hot for planets, but hot enough still to excite and ionize hydrogen. And so this can manifest in spectra in the form of H-alpha emission. And so a member of our team, Yifan Zhou, had followed this up with HST and identified this point source, which should be brighter than the surrounding material if indeed the H-alpha emission is from the accretion onto the planet. However, that was not necessarily found. And so what this could potentially be might actually be like scattered light from the central star off of like a disk clump. However, when they compared the emission from the H-alpha, the H-alpha emission from the protoplanet candidate and the star, they found that those were consistent but taken at different times. And they weren't able, because of the observing method that they used, they couldn't necessarily compare it to the surrounding material in the disk. So they compared it to the star. And they couldn't say for sure whether or not it was coincidental that the emission strength in H-alpha of the star and the candidate were the same. And so this led to a follow-up project in a different emission line. This one is currently in prep. My team and I observed the same target with NERC2 on Keck in the Passion Beta narrowband filter. And so what we're seeing here is the PSS subtracted image on the top, and then the signal to noise map on the bottom. And surprisingly, we're kind of scratching our heads now. Now we actually don't detect emission at all, whereas we do detect emission on the star, which would indicate that, okay, maybe instead of a scattered light scenario, like was suggested by Zhou et al., maybe this is a bona fide accreting protoplanet maybe the H-alpha emission is centrally located. If there's H-alpha emission at all, maybe it's being obscured by material around the planet. Maybe this is just a period of time when the planet isn't accreting, if it is a planet. However, as we eventually write in the conclusions of this paper, which should be published sometime early next year, the signal to noise for our measurements of the star at the same time of observing the planet were too high to distinguish between either. So essentially, we hadn't detected H-alpha emission, Passion Beta emission. Okay, so we still don't know the nature of the source, and it's really important that we follow up on this object so that we understand better how planets form. So our team has devised a new plan that takes advantage of light echoes. I have here on the right a sketch of a star. This could be AB Auriga, for instance, with a circumplanetary disk and there's accretion streams from funneling material from the disk onto the star. And at the base of that accretion stream, we see a accretion hotspot, similar to that previous sketch that I had shown. And this is typically brighter than the whole rest of its environment. And so the light from this accretion hotspot is emitted in all directions. One of those directions is to the observer, and another direction is toward the disk, where it impacts the disk and then is scattered in, again, all directions, one of those directions being, again, toward the observer. However, the major difference here is that there's a time delay. In the case of AB Auriga specifically, that time delay is about 10 hours. And so the way that we can use this mechanism, which I have just outlined, to confirm or refute the nature of the protoplanet is by assessing the brightness of the star over time and the brightness of the candidate over time. And we should see if the, let's say that the candidate is scattered light and not actually a star, we should see that the candidate brightness and the star brightness are correlated, taking into account that time delay. But if we find with that plot on the furthest right, that if they are uncorrelated, then this supports the accreting protoplanet scenario, because it should be the protoplanet, if it does exist, should be locally emitting in such a way that is different than the star. And that could be, that would be the first time that a planet would be confirmed using light echoes. And if we do, in fact, that's the case, then we will have established a new confirmation method that can be used on a swath of other systems. However, this requires that we understand very well the accretion behavior of the central star. And that's where we come in. So our team has worked with y'all at AAVSO and very closely with Walt Cooney to devise a ground-based monitoring program where we can monitor the brightness of the central star over time in support of that HST experiment I had outlined. The filters that we are asking for specifically are B, V, R, and H alpha, with emphasis, however, on H alpha. Because H alpha is a tracer of accretion, that bandpass will be the most effective at distinguishing light changes actually in light from the star. And then R is also, like, let's say you don't have H alpha, if you have an R filter, that one I would say is secondary, because H alpha line is within the bounds of the R filter. We also ask for B and V because that would help us get more color information, which can help with other goals of the program in addition to this one, which I'll outline in a moment. But H alpha filter for the observers who do have that is definitely preferred. And then for each of the observers, we're asking for a cadence of 1 to 5 images of AB Auriga per night. And we would like that during the HST observations. And we have the dates. I'll go over the dates, and then I believe we have alert notices as well through the AAVSO for when those are going to happen. And then we would also like AB Auriga to be monitored over the short and long timescales. And so what I mean by short timescale and long timescale, because that can be relative, if you have an H alpha filter, then short timescale would mean like minutes to hours per night. So that would mean many more than 1 to 5 images per night. And then long time scale would be, we would like this to happen over several months. And that's important for many reasons, which I'll get to. However, if you do not have an H-alpha filter at hand, the cadence then would still be 1 to 5 images per night with B, V, and R. The reason being is that the this, and I'll go over this as well. I keep saying I'll go over this, but we'll definitely get there, and you'll see with your eyes that it's more difficult to distinguish variability with these broader band passes. And so like the use of resources would make most sense if observers were to acquire an image 1 to 5 images per night. So that's what I mean by short and long time scales. For those with broader band passes, short would mean maybe like 5 images per night, and long would still mean months. But if you have H-alpha, short is like as often as is reasonable to you. So just to outline one more time, the primary goal is to characterize accretion activity in support of the light echo experiment with HST. Also, massive accretion events can occur, and we don't actually know how often they occur. That's the problem. So here is an image. It's a spectrum of the H-alpha line for this central star. And what Costigan et al. Had done was they monitored AB Auriga for 1 hour for 4 nights in a row. And on night 3, what they found was the strength of H-alpha line had changed significantly within the course of an hour. And so this shows that like events like this can happen, but we haven't in all of our monitoring since, which is at least with spectra, is not as extensive. And so we really, at this point, we can only say that we have a not as good of an understanding of how often this actually occurs. But the primary thing is that if it does occur and it happens during our HST run, we need to know. And that will have massive implications for what we can conclude about the nature of the accreting protoplanet. There's also other science that we can do with this program. We can characterize the accretion activity over short and long time scales as well. And the reason we want to do that is because we also really don't understand how intermediate mass stars accrete. So for low mass stars, we are pretty familiar with their accretion mechanism. It's called magnetospheric accretion, where the very strong magnetic field of the central star can interact with the circumstellar disk and funnel material along these strong magnetic field lines onto the star in a relatively ordered way, not always, but mostly. And this causes those hot spots at the foot of those accretion streams. However, for intermediate mass stars, we're not sure if this is actually the case. It could be magnetospheric accretion, but it also could be this thing called boundary layer accretion, where the circumstellar disk really leads right up to the surface of the star and accretes directly through contact at this layer called the boundary layer. And that's where we would see this extremely hot material that would then ionize or excite those hydrogen molecules, which would then generate H-alpha. So H-alpha emission. So both of these mechanisms would result in the same type of emission, but the variability signature would most likely be different. And so that would be just another science result that we could pull out is identifying exactly what is the mechanism by which AB Auriga accretes. And this helps us bridge the gap between low mass stars, the accretion mechanisms of low mass stars and high mass stars. So this could be, this would bridge the two. And so it's very important for that reason. Additionally, and Walt pointed this out to me, which I was really grateful for, there are rare dimming events that have occurred on AB Auriga. And this would indicate that something is possibly eclipsing the star. And so this is something that would be really neat if we were able to catch. They happen, I guess we do have sort of a sense or a one data point for how often they occur. This person, John Toon at this website, had shown this image in 1997, showing this massive dimming event, and refers to another one that had happened in the 70s. And so they happen at least, or maybe at most, every 20 something years. But that is an upper bound. We don't really know if those happen as frequently in the space between 0 and about 22 to 25 years. So this is just another science result that we may be able to pull out of contributions from AAVSO observers. Just more science. And so what have we so far? Last spring and winter, we sent out our first alert notice asking for monitoring efforts of AB Auriga in the band passes that I had previously described. And here are the results for our B light curves. I have color-coded the observing code, or like the data points by the observer's code, and at least for the observers who had contributed 20 or more individual observations. These would be considered active observers, but those points that are in white are a combination of observations from many observers whom I have listed above here. And that's consistent among all of the observations that I will show. So I here show on the left the date in the x-axis and the B magnitude in the y-axis. These are unbinned observations. If you see an error bar on some of the data points, that is because there were uncertainties reported with the data that were downloaded, that were downloaded from the AAVSO website. Not all data points had uncertainties reported, but for the ones that did, I included those. And then on the right-hand side, I binned the data into nightly bins to give us another look at it from a different perspective. So here you can especially see like that orange data point, or like the several orange data points around March 9th. Those are condensed into a single data point. And then here are the V band observations from the active observers are given just above these two plots. And there may be hints of an interesting dimming event, but I mean, something like this could be a weather event as well. We would need to, and this is just like a preliminary look at the data. So like, there's no conclusions that we can make of anything at this point without like further in-depth analysis. But same as above, the left are the unbinned data, and then on the right, we have binned nightly data. Okay, and then here are the R band observations. So the R band does contain the H alpha emission line. Here on the left, same as prior, we have the unbinned observations, and then on the right, we have nightly binned observations. And then the H alpha data. On the left are the unbinned, and then on the right are the binned. I've also included data from AAVSO Net that were provided by Walt. And those are just a different shape to distinguish them among the rest. And then, yeah, so there's a lot to think about here, because one of the things that through our discussions we've seen is that there isn't like a whole lot of distinguishing features in the light curve, you could say. Like someone might look at this and say, that's flat. That is not exciting. However, it does tell us something. What this tells us is that it gives us a lower bound for the brightness differences that would be caused by an accretion event in terms of the brightness, but it also gives us a bound or some insights as to how often stronger events, stronger than that lower bound, would occur because they would have not occurred. And so within this amount of time. So we can say, okay, well, here are observations that were very consistently observed for this amount of time. Maybe massive accretion events are rare. However, there were observers who would, there wasn't as much consistency among the strategy of the observers, I think. And so there could be systematics that are involved that may be contributing to the brightness that they report. But as far as we can tell, we would need another full season of observations to know for sure whether or not those massive brightening events or dimming events can occur, at least on these timescales. Yeah. So, okay. So to kind of review and set expectations for like when exactly the HST observations would happen, because that is, those are the most crucial time periods where we would really like all hands on deck staring at AB Auriga and helping us, especially during the HST experiment, what is happening to the central star, because really our results of that experiment hinge on what we know the star is doing at that time, or leading up to that time, and then shortly following that time. So in 2023, we pointed with HST at AB Auriga in January, February, and March. And the current plan windows for 2024 occur over much broader windows. These usually like about a week leading up to the date that it will actually happen. We get a notification from STSCI and NASA saying, okay, like we're observing at this time, and be prepared. And so that we say, great. But unfortunately, I am not able to tell you exactly which day it will happen in one of these windows, but it will happen in these windows. Oh, and when we do know, we would send out an alert, and so you would definitely know. I also wanted to mention spectroscopists are also welcome. So far, I've focused primarily on the photometry because up to now, it has been mostly a photometric campaign. We have a parallel campaign going through UT and McDonald Observatory, where we're collecting spectra with the Toll spectrograph on the 2.7 meter. And so I have some of those spectra here overplotted. They're color-coded according to the day that they were observed. And some of these data were all taken in a single night. Some of them were taken like a day apart. Some of them were taken a week apart. And so, at this point, we've just been able to plot up the data, but we're hoping to do a full analysis in combination and alongside the photometry. But we also have learned that AAVSO has spectroscopists too, who can also contribute to these efforts in parallel. And so right on the right is a spectrum from observer GKEA, who is Kevin Gurney. This was provided by Lauren Harrington. And if you are a spectroscopist, and if you have the resources to provide a spectrum that looks like this would be amazingly helpful in monitoring the accretion activity. We can draw very precise accretion luminosities from data like this. And so welcome, join us if you want to. Join the dark side, we have cookies. These would be great as well. So just wanted to throw out an announcement also. So returning to the photometry program, I'm just going to summarize what we're asking for and the times that we're asking for it. So just to review, the filters are B, V, R, and H alpha, and cadence are 1 to 5 images per night. If you have an H alpha filter, then we would ask for a higher cadence at your discretion, how often you want to observe it. If it were every few minutes, if it were every hour per night, that would be helpful toward the goals of the campaign. It's really important that we observe during the HST observations. So please keep an eye out for an alert notice when we know more about when those dates are actually going to happen. And then we also would like to observe AB Auriga over short and long timescales. So that's why we're asking for a whole observing season, is because if we observe it on the short and long timescales, then we can say something about what the exact accretion mechanisms are. We can map that to like the material flow and mass flow around the star, and help us understand more about how intermediate mass stars gain mass and evolve. And also it would help us identify and place bounds, potentially, the frequency at which these massive accretion events can occur, and then also these seemingly rare dimming events. That would be incredibly exciting. And I wanted to stress that there have been some changes from our original alert notice. Prior to the most recent notice, we had asked for the comparison star to be star number 116 here, but instead, Walt did a really nice analysis and had identified that potentially 104, highlighted there by the green circle, is the most better suited of the two to being your companion or your comparison star. And just wanted to stress also that consistency among observers is very important. And so this can help us identify systematics of the observations. If every observer is doing something different, it makes it more difficult to compare the entire data set as a whole. And so it is quite important that if you do choose to participate in our program and make contributions, that you do use the comparison star shown here on the right. And with that, I'm happy to take any questions, and thank you.
Wow, thank you so much, Lauren. Excellent presentation. Okay, so we have got a lot of questions in the queue, so let's dive right in. Our first question comes from Kenneth Menzies, who asked about the recommended cadence of 5 images per night. Does that mean, say, 5 images taken each an hour apart, or are you referring to taking like 5 images in short sequence and then averaging them together so you get a magnitude with an associated uncertainty? Could you elaborate on that?
That is a great question, and I'm glad you asked that because it's important that I clarify. When I say 1 to 5 images per night, I was referring to 5 images spread throughout the entire night. However, the signal to noise of just the companion star, sorry, I keep saying companion star, the comparison star is significantly dimmer compared to AB Auriga as well. And so you might have to, in order to produce one image, as quoted here on the slide, you may have to take several images and then stack them to achieve the signal to noise that we are looking for. And so to repeat what I said, 5 images, final images spread throughout the night, but each image might require to achieve signal to noise of like at least, I mean, we were aiming for 50, but even if it just the high signal to noise that is possible, you might have to take a few and then combine them.
Okay, thank you. So let's see. Our next question related to the comp star. So we have some people who are wondering what makes the difference between star 116 and star 104? Why is 104 so much better?
That might be a question that Walt might be able to describe more. He has been our leader in comparison star analysis. Are you there, Walt?
Yeah, now I'm unmuted. Yeah, so, comparison stars are an optimization problem. We asked for 11.6 last year because it's very close to AB Auriga. And so for people who had small fields of view, then it was going to make it available for everybody. But of course, the problem is just that it's even that much fainter than the target star. And I took a lot of my images taken with various scopes and that had enough field of view to get the 10.4 star. I don't remember exactly what the color index difference was between 10.4 and 11.6. I don't think it was tremendously different, but you had much more signal to noise, obviously, with the 10.4 star. And meanwhile, as you saw from the figures, AB Auriga is running 6.5, 7th magnitude. And so anything you can do to get a better comp star with better signal to noise, it allows you to sum fewer images to try to get 50 or 100 signal to noise for your comp star as well. And we should probably mention too, there's one big bright star right next to AB Auriga there that seems like the world's most perfect comp star, except that's SU Auriga. And, variable stars don't make ideal comp stars. And as a matter of fact, a number of folks reported SU Auriga to the AAVSO as part of doing their data reduction because it was right there. And that's certainly a good thing to do. There were several other variables in your field of view, depending on how large your field is. So anyhow, I hope that helps. It's really based on most possible signal to noise. The distance between AB Auriga and the 10.4 comp star is 16 arc minutes. And so if you've got a field of view that gives you 20 or better, you should be able to do it. Anyhow, I hope that answers.
I think so. Thanks so much, Walt. So there is a related question, which you just nicely kind of segued into. What should you do if your field of view is smaller than that and you can't fit both the target and the comp?
Well, in that case, then I would probably go back to use 11.6. We've got a lot of data from last year, and so at least it's comparable. Now, a lot of folks did use, honestly, different comp stars, or they used ensembles, or they used all kinds of different things. But we really are asking folks to try to do everything in the same way. If your field doesn't allow 10.4, then yeah, let's use 11.6. Thanks.
Okay, great. And one more question on the topic of the comp star. We'll jump to this one since we're already on it. Kenneth Menzies was wondering, why not use the star 7.6 since it's a closer magnitude and brighter?
Yeah, that's a good question, and I don't remember the answer. I tell you what, Ken, why don't we go on and let me look at that again real quick and see if I can come back to you.
All right, that sounds great. And just let me know whenever you're ready to come back to that question. Okay, so shifting
Oh,
topics here.
actually, sorry, I do remember. 7.6 has another one of those little inconvenient things. It is also a variable star.
Oh, well,
Yeah, it's a comp star that's been on the AAVSO comp star list for a long time. As part of doing this work, we realized that, hey, it's a little bit of a macro variable. I think the variation was something on the order of 1/10 of a magnitude. And so what the chart team did is if you go to this sequence, maybe an updated chart, and then go to the photometry notes, it'll tell you that that star should be used for visual only and not for photometry. So they chose not to take it out of the database because people have been using it as the visual comp star for a very long time. And actually, Brian Kloppenborg, if you see in the notes, has noted that yeah, the variability is 7.55 to 7.64. So we've got an automatic 1/10 of a magnitude built into that one, unfortunately.
I see. Okay, well, thank you for that answer. And actually, we did have a comment come in on the topic of the comp stars. This is from James McMath, who just recommended to the observers out there that if you're working with a tight field of view, go ahead and move the target area to somewhere halfway between AB or and the comp. Doesn't have to be centered for good data quality. Okay, so now we're going to go to some of the questions about hydrogen alpha observations because we've got a lot of curiosity about that. One question which I've seen pop up a bunch of times is about the filter bandwidth for the hydrogen alpha filter. Is there anything that should be taken into consideration there? Is narrower better or broader? I think I saw one person was mentioning having a 20 nanometer bandwidth and a 7 nanometer bandwidth available. Any thoughts on that?
The more narrow the bandwidth, the better. I can see that potentially causing issues though with the comparison star, as it's not outputting as much light in all band passes really, as AB Aurigi. And so I wish I had like a concrete answer to give. It might take some experimentation. Walt, I'm not sure if you have any other insights that you might be thinking.
Walt, you're muted.
I had the same question too along the line, and so I called 1-800 Arnie Hendon, who's he's been doing photometry for forever now, and his comment is yeah, there can be some effects there, but they're very small, and that he just really wouldn't worry about it. And I see Brian Skiff is with us too, and Brian is someone else who's done photometry forever and a day. Brian, would you add anything to that?
I know
Can Brian talk?
Since he's logged in as an attendee, no, unfortunately Zoom webinar doesn't give the option for attendees to unmute, but feel free to drop something in the chat, Brian, if you'd like, and we can read it out. Okay, so while Brian is typing or not typing, I have a related question about the hydrogen alpha photometry. So Andrei Kovacs had asked about, well, first of all, about the plot that you showed, Lauren, with the hydrogen alpha data. Andre was curious if those are instrumental magnitudes, and specifically, he's wondering that because we don't have comparison star magnitudes with a hydrogen alpha filter. So, related to that, what should you use for your comparison star magnitudes?
Can I jump in?
Yeah.
Yeah. Hey, Andre. RC. apparently, and I had never done hydrogen alpha photometry before either, but the common method for doing hydrogen alpha photometry to find a 0 point is use the Cousins R magnitude for your comp star. And so that's actually listed for this 10.4 star. That numbers, we actually printed that out in the alert. And for those who aren't familiar with it, you can also pull that up in the AAVSO on the variable star plotter. You click photometry for this chart. When you're that's a link above the chart itself. And then you also have to tell it which filter band passes that you want, and it will give you RC comp star photometry.
Okay, thank you. Alrighty, so going back to the question about hydrogen alpha filter bandwidth, Brian Skiff did have some comments. He asked Lauren if she could pull up her hydrogen alpha spectrum slide, and then if we can just take a look at, how does the filter bandwidth compare to the actual width of the hydrogen alpha line. Okay, cool. So 7 nanometers would work out to 70 angstroms, and it looks like the line is quite a lot narrower than that. So a 7 nanometer filter should capture the whole thing. Brian Skiff also said, if one does use one of the hydrogen alpha filters, it would be good to also take some data with the wide RC filter so that you have some idea of the amount of H alpha contamination. All right, thank you so much, Brian, for sharing your expertise on this. So, just taking a look now to see if we have any remaining hydrogen alpha filter questions. Yes, okay. So Nicola Antonov on Facebook asked if hydrogen alpha can be transformed to RC. And does that make sense considering transformation coefficients?
Well, Nicola, I think the answer to that is probably no, because it's you're effectively transforming an emission line to a broad spectrum, and so if there are things going on, it's kind of not fair to call that to be able to do that. I would say, and maybe not everybody's familiar with it, that you can report it as H alpha directly in the AAVSO, and I think that was news to many of us. We're used to BVRI type photometry, but you can choose to report it as an H alpha .2, and that was all those graphs that Lauren showed us. I hope that answers your question.
Great, thanks so much, Walt. So, I think that all we have left on the hydrogen alpha photometry topic is just a comment from Chris on Facebook, who said that this is a really interesting campaign to see for the reason of requesting hydrogen alpha photometry. And there are many more amateur astronomers out there who own hydrogen alpha filters than those who own Johnson Bessel filter sets. So this could be broadly applicable.
That's great to hear.
Okay, so moving on now to other questions about filters. We have one here from Bart Stales, sorry if I mispronounced your name, who says, who asks if the Sloan R prime filter would also be of interest to this campaign.
I think we wanted to focus on Cousins R filter. I'm not sure if I have like a solid idea of how we might analyze that in a uniform way with the rest of the data that are taken with Cousins R. So if you have Cousins R, that would be preferred over other filters.
All right, thank you. And then our next question here comes from Nicola on Facebook, who asks, would doing a longer multiband observation, taking a few hours in one night and alternating B, V, and hydrogen alpha, just for example, would something like that be of interest? Hitting multiple filters in the same observation?
Absolutely, using multiple filters would be of interest. What would be the most useful arrangement would be to, instead of doing like all B one night and all V one night and all R, instead alternating in a single night as close together in time as possible, because that can help us pull out the like B minus R colors, or like different colors at that instance in time. So it'd be like B V R, then B V R, B V R in this like grouped very closely.
Okay.
One other thing about that too, you might consider for each one of those filters as you rotate through, you might have to take 5 or 8 or 10 short Bs and 5 or 8 or 10 short Vs and Rs, just so you can stack them individually enough that you really are getting, like Lauren was saying, the single image final data point with high enough signal to noise. So if you can do that, that might be the better way for each data point to have more significance and to show overall movement over the course of the night better.
Okay, thanks, Walt. Okay, and on the topic of stacking, actually, so John Pickett had asked what stacking methods will improve the signal to noise ratio when working with this degree of brightness differential. John says that he normally only uses a standard average stack when shooting this star.
Hey, John, I just averaged 2. There are arguments for others, and those are all good arguments. There's median combine, and there are other fancier ways to do like sigma reject type stuff. Average works pretty good. Lauren, any?
Yeah, I would say for consistency's sake, it would be ideal if averaging is the primary method that they should be combined. Yeah.
Okay, great, thank you. And also related to, well, actually, on that topic, we had a comment from Jeff Myers who said that stacking just using a normal average algorithm is also guaranteed to be a linear combination. So cool, thanks for sharing that, Jeff. And then a question from Jeff on the topic of stacking. Is it standard to report the time of the observation as the midpoint of the overall stack?
Yes, yeah, that's right.
Okay.
You should report as the middle of your summed exposure or averaged exposure.
Makes sense, thank you. Okay, and now let's move on to some questions related to the professional side observations for this campaign. So first we had a question from Chris on Facebook, who was curious about, the brightness of ABOR. He asked, at magnitude 7, isn't it too bright for Hubble to even look at?
At the exposures that we are using to observe the companion, yes, the star saturates. But you can take a very short exposure and the star will not saturate.
All right.
I wonder real quick if that's also related to the fact that when we're doing cataclysmic variable stuff and supporting HST observations, we specifically try to give them the shout out if a CV goes into outburst so they don't damage Hubble. But that's a different instrument. That's the cosmic origin spectrograph that's being used. And so that one can be damaged by a star that's too bright. And while this is a different instrument, I take it, Lauren?
I believe so, yeah. I think it was the wide field, or sorry. I don't remember exactly.
Yeah. but
It's
it's not the
definitely the sun, yeah.
spectrograph. So
And actually, a note, speaking of saturation, a note for spectroscopists, if they decide that they're interested in contributing to this program, the H-alpha emission line itself can saturate very easily. So I caution you when observing this star, we try not to, I guess, double check that the line isn't saturated at the beginning of your run, just so you can make the adjustments that you need to.
Great point, Lauren. And just adding on to that as a spectroscopist, you know, of course, look for if it's flat topped, that definitely means it's saturated, but the same considerations apply here as with photometry, where you also don't want it to go into the nonlinear regime of the chip. So try and keep it, you know, let's say 40,000 ADU at max and below is you're definitely safe there. Of course, it depends on your specific camera, but yeah, great recommendation there. Okay. Speaking of spectra, why don't we head over to one of those questions? Andre had asked if spectra should be calibrated in units of absolute flux for this campaign.
I don't know. I need to think about it. We would usually we're going to end up normalizing it anyway, actually. So probably not.
Okay, good to know. I guess a different question that has just made occur to me is, are you expecting the continuum flux from AB or to be varying at all? Or is it just the hydrogen alpha line that you're expecting to see variation in?
There will be variation in the continuum flux. This is the, yeah, yes, is the short answer. There will be variation in the continuum.
Okay, good to know.
Uniformly, mostly though. It'll all kind of rise and lower together.
Good to know. In that case, it does sound like absolute flux calibration would be, I mean, it wouldn't hurt. I'm going to say to Andre, you know, if you have the capability to do that, go ahead and do that because it doesn't hurt. But, you know, it's good to know also that the spectra may be useful even without it, because I know it's a difficult procedure to do.
Absolutely. That is a good recommendation. Thank you, Lauren.
Thank you. Okay, so speaking of spectroscopy, I was curious about, you know, how rapidly does the hydrogen alpha line change? Like you showed there was sometimes variations in a single night. Do you ever get like flickering that would be relevant on timescales of a single exposure?
I guess it depends on how long your exposure is. What would be reasonable would be no more than, oh gosh, and you know, I'm just like, my mind's thinking about all like the different possible setups and the different apertures. So I'm not even going to quote a number. But I would say that anything that is significant would probably happen in tens of minutes. The one instance that we have observed, I'll go back to that slide here. This night had what they label here in the colors, beginning with a red 0 and then moving up to that like lime green 31. Those are at the minute marks within the hour that it was taken. So it can happen very fast. So it can happen noticeably with five minutes. But if you have to expose longer than that, you would notice a difference at a half hour or 15 minutes. So this is the one instance that we do have measurements for. That's not to say that it can change more than this or faster than this. And so that's one reason why the work with spectra would be important as well. It would help us nail that down.
Okay, great to know. Great to know. So usually, when I am shooting spectra, I would try to average together, 1 or 2 hours of exposure just to get the signal to noise ratio to be as excellent as I can get it. It sounds like though for this target, would you recommend, you know, maybe you take 1 or 2 hours of data, but then you stack it into 30-minute or 10-minute individual spectra and submit those? What would you recommend?
I would go off of the signal to noise that we're looking for. We're hoping, I would say, like a signal to noise of at least 50 would be ideal in terms of distinguishing the variations that would be then comparable and that we'd be able to analyze with the spectra from our UT campaign as well, because we would put all the spectra together and analyze them all together. And so yeah, if you can, whatever setup and steps you need to take to achieve a signal to noise of 50 about, then I would.
Uh-oh. Lauren, are you still there? Uh-oh. I think we may have lost connection with Lauren there. Okay, well, this was mentioned that there was a bit of instability in her internet connection earlier, so we have a backup plan. She should be logging back on in a minute through an alternate connection. In the meantime, I appreciate your patience. I'm going to take this excuse to go catch up on, I think I saw some questions coming in on the Zoom chat. Make sure I don't miss any of those. Yeah, there we go. Oh, hi, Lauren.
Howdy. I'm back.
Great. Glad it was only a short drop out there. So,
Oh, me too.
you want to continue where you left off?
Yeah, so I'll share my slides again. Actually, I don't remember what I was saying. Will you help me remember my last few words?
I got pretty alarmed when you dropped off, so I forgot your last sentence too, but we were talking on the general topic of exposure times for like spectroscopic cadence for seeing the hydrogen alpha line variations.
Yes. So essentially, I think the bottom line of what I was saying was whatever procedure you would need to do to accomplish a signal to noise of, I would say, 50. That's what you need to do, and that might vary from person to person. So,
all right, sounds great. Thank you. So, let's see. I think we should go back to photometry questions for a little bit because we did get several of those in. First question from Gary Shaw. Gary was wondering if there are any issues which we should take into consideration related to atmospheric scintillation. Is there some minimum exposure length that everyone needs to aim for?
oh, not that I know of. I mean, like, I'm sure there is, but it hasn't been a problem so far. Walt, what's been your experience with that?
The recommendation I hear a lot of times from the Arnie Hintons of the world and the expert folks are 5 seconds is probably a minimum time to reduce scintillation noise, and so 5 seconds, maybe 10 seconds is even more conservative.
Thanks, Paul.
Great, thank you. Okay, and another question here. This one comes from Tony Vale, who asked, are you looking for transformed magnitudes?
I'm not really sure if I understand the question. What do you mean by transformed?
A color transformation for the broadband.
Oh,
And I think the answer is probably yes. Although I'm a little slow to say that because we're trying to compare everyone's data. That's what transformation helps you do, but only some people will be able to do it. Maybe the answer is yes, and that will make your data potentially more valuable, more consistent with other folks' work. We did already talk about transforming H alpha to RC or to some standardized H alpha, and there really isn't a way to do that.
Mhm.
But for the BVR broadband filter work, you could.
Okay, good to know. Thank you. All right, and let's see. Next question here. So this one goes back to the pro observations. Mike Poxon, who's the leader of the Young Stellar Objects group here at the AAVSO, asked, so because the circumstellar disk of AB Auriga is tilted a bit, are you planning to make any polarimetric observations during this run?
We are not, no. We're primarily focusing just on the H alpha brightness of the companion and the star, and yeah, so no, sorry.
Okay, good to know. Thanks. All right. Oh yes, we did have a comment here from Dr. Brian Kloppenborg, who is here in the audience, and mentioned that he would always encourage people to transform their data whenever possible. So that's going back to the previous question. That's the understanding I've gotten too from recent discussions at the AAVSO annual meeting. Okay, so I'm gonna make sure I'm not missing any questions on Facebook. Nope, I'm not. So we're down to the last couple here in Zoom. Richard Berry had asked if the accretion hotspot flickers or flares on short time scales.
Yes, it absolutely does. And we've seen this in light curves from space telescopes that have been able to achieve very high precision, very, very short cadence light curves. And we see that within minutes, it does flicker in some sort of like stochastic way on short time scales, and then that follows with larger trends. And so I don't believe that our ground-based observations will be able to distinguish that flickering. It'll be buried in the uncertainties. And but yes, absolutely, when observed with space telescopes, you can see that the flickering does occur.
Okay, thank you. Okay, and looks like our last question here comes from James McMath, who would just like a quick clarification going back to that question about the hydrogen alpha filter bandwidths. Was the ultimate decision that the narrower hydrogen alpha filters are superior to the wider ones?
Narrower would be able to help us just so essentially the light that you would be collecting, a larger fraction of it would be within the H alpha emission, as compared to a wider bandpass. It would be relatively less H alpha contribution of the total light that you're collecting. And so since H alpha specifically is what we're trying to characterize, the smaller the bandpass is around the H alpha line, then you're more likely to see significant variability that would be caused by accretion. Yeah, but I think it also really depends on like, can you achieve that using that short bandpass where you're collecting ultimately less total light? Can you collect sufficient light of the companion or the comparison star. That I think is where the challenge will be.
Okay, thank you. All right, so that was our last question. So I'm going to go ahead and put up our closing slide here and start with the most important announcement, which is that I want to extend an enormous heartfelt thank you to both Dr. Lauren Biddle and Walt Cooney for sharing their time and knowledge with us today. I mean, this has been a seriously excellent webinar, and I really appreciate you taking the time, Dr. Biddle, to teach us so much about this project.
Thank you so much for having me. I'm honored to be here, and it's been a blast working with the AAVSO, and the data that come out of AAVSO are so valuable for science, and I'm grateful that for the contributions from the community, and excited to continue working with y'all. Yeah, in return, thank you for having me.
Wonderful, thanks. Okay, and to continue our closing announcements, I would also like to thank again our sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. And next, I would also like to thank everyone who showed up in the audience today. Your observations are fundamental to this campaign, as you've just seen, and it's your participation in all of our programs which allows us to keep growing, keep educating, and keep making an impact on variable star science. So thank you, each of you. We're so grateful for your support. Now, luckily for those of us who want to go back and review the observational requirements, today's broadcast has been recorded. So if you want to find it right after the webinar ends, it will be automatically uploaded to our Facebook page. That's facebook.com/AAVSO. Pretty soon, we're also going to upload it to our YouTube channel, where it will join an enormous library of educational videos. You can find our educational YouTube library by going to the YouTube website and searching for the username AAVSOHQ. Also, when you log out of the webinar today, you should be automatically redirected to a survey. I would really appreciate it if you could fill out the survey, let us know what you thought of today's special broadcast and what we might be able to do better next time. All right. To close, I would like to express one last huge thank you to Dr. Biddle from all of us here at the AAVSO. We appreciate you.